All right. This is either a positive or a negative, depending on how you feel about jokes, but this is the last lecture in the mini course on theoretical neuroscience. It's been a great week. So all of my lecture slides and handwritten notes are posted online. There's a readings folder for my section 2 that I have included a paper from Marcus Meister and Tim Gollish, I Smarter Than Scientists Believed or something like that. It's a really good review article about all the funky nonlinear things your retina does. Your retina is not a camera. That's the point of that. So have a look there. I have posted solutions to the exercises that go with each lecture. The solutions for 1 and 4 are really nicely teched up and have been, sort of scanned for errors. The one for 3 is handwritten and a little bit of a mess, and the one for 2 I realize I have a piece of and not all of, so I'm going to scribble that down and put it up. Hopefully, if anybody feels like they want to scribe that and turn it into a LaTeX doc because you can't handle the handwritten stuff, please, you're very welcome. And if you have any questions after I'm gone, feel free to send me an email. That's how you find me. There's the internet as well. Okay, so this is our last chance for jokes. So how many people here consider themselves a biologist and only a biologist? Ha, good. So a mathematician, a physicist, and a biologist are asked to prove or disprove the following theorem. All odd numbers are prime. The mathematician, all odd numbers are prime. Mathematician says, 9, leave me alone. The physicist says, all right, I gotcha. 3, prime, 5, prime, 7, prime, 9, experimental error, 11, prime, 13, prime, 15, experimental error, 17, prime, 19, prime, 21, we have a problem. The biologist is asked the same question. He says, I should make it. I didn't want to make him a gender. No, okay. She says no, then it screws up. Okay, 3, prime, 5, prime, 7, prime, 9, prime, 11, prime, 13. So on and so forth. All right, we're moving, we're thank you. I'm sorry, biologists. I am very glad none of our seminar speakers are here right now. Please do not point anyone to this YouTube video. Okay, so I have a...
Phil Bialik, right?
What?
Phil Bialik is one of our seminar speakers.
Aww. Aww. All right, so I have 2 more jokes for you. These are a little bit off path, but they're in honor of Thierry, because I always try to speak a little French, and my accent is so bad, he usually thinks I'm making fun of him. So I'm going to go for it. Why does the Frenchman eat 1 egg only for breakfast? Because it's enough. All right, now you can translate that joke into German and make it completely like just obscure and nonsensical, which I think is fun. Okay, but my favorite French joke is this one. René Descartes rentre dans un bar et le barman lui demande, vous prendrez comme d'habitude, René? René dit, je ne pense pas. Et pouf, René désespéré. If you did not get that joke, then I go to Thierry and he will explain it to you. Okay, so last time we were talking about efficient coding in neural systems, and it applies very broadly. So the response doesn't have to be spike or no spike from a neuron. It can be whatever you want. And so this information theory can apply to all biological systems, and your fearless leaders are some of the folks who have spread that beyond just neuroscience into developmental biology and into the immune system with beautiful results. So you can take this farther. What I want to do today in this last lecture is to talk to you about the information bottleneck approach. And first I'm going to give you a lightning fast intro to channel coding. And again, if you want to know more, if you want to know like the nitty-gritty proofs of this, that would take us the whole lecture, and we just don't have the time. So I'm pointing you to Mackay's online lectures again for that. But I'm going to sketch the main results here. I'll try to do everything on this board, and then the notes are already posted online if you want to follow along there. So we're going to do our very last chalkboard interlude. All right, good. So here we go. So when we've been setting up all the problems here, we've had a input information source. And that's very general. And it's why all of these ideas from information theory could be ported from communications theory into biology so easily, because there's nothing here about mechanism. So for what it's worth, this is a phenomenological way of evaluating a system, and it's pretty darn good. So we've been thinking about a source that then gets input to, say, our biological system, where that information is compressed. And all of the source coding theorems of information theory, the source coding theorem of information theory tells you how many bits you need in this compressed representation to represent the source in a lossless fashion. Okay, so that's a result that is fairly easy to derive, but would take a lecture. Then, after it's compressed, we think about it going through an encoder, and the encoder's job is to organize this representation in such a way so that when this information is sent down a noisy channel, it can be decoded without error, or with minimal error that we specify. So there's a decoder that lives downstream of the noise. And of course, after the message is read out, you're going to want to decompress it. And then you might want to do something with it. So maybe, behavior, if we're a neural system. So this is using it. So all of this part about how to compress and decompress has to do with the source coding idea. And there's a source coding theorem associated with that, which tells you basically how big this compressor has to be if you don't want to lose any information about the source. And all of this stuff about how to encode and decode if you're sending things through a noisy channel is channel coding. And there's an associated theorem that goes with that, which, I feel like I just lost some hair cells. Oh my gosh, that was a terrible noise. And I'm going to sketch the channel coding theorem here. Okay, so the channel coding theorem states, for any discrete memberless channel, there exists a capacity greater than 0, called the channel capacity, such that for every epsilon greater than 0 and for every information rate less than c for large enough n, there exists a code of length n and transmission rate greater than or equal to c and a decoding algorithm such that the max probability of bit error is less than epsilon. May I draw you a picture that will make this a little bit simpler? So I have written this down. It's online. I am not going to take 5 minutes to write that on the board. Instead, I'm going to draw you this picture. So we are sending messages through this noisy channel, and we want to make sure that we can read them out. Okay? And so what we have here on this axis, I'm going to call this R, and this is our information rate. It's how much information we get through the channel. And here is a sweet spot, and that is the channel capacity, and that's labeled C. Channel capacity. Now, why is that a sweet spot? Because of the y-axis. The y-axis is the error. And when you're doing things in information theory and you're following stuff in Mackay or in Cover and Thomas or whatnot, this is usually called PB, and that's the probability of bit error. That's I send a 1 down this channel and it comes out a 0. It's a bit flip error. And here is a special point. That's 0 error. Okay? And what the channel coding theorem tells you is that up to this special point, the channel capacity, all of this region is allowed. Yeah, Atos. That is this special point, and I'm going to define why it's special, because after this point, you can't get down to 0 error. And this line is you have to figure out what this is as a sort of theoretical optimum for your particular channel, and that's defined by rate distortion theory. So the amount of error you have distorts your original input. Here you have zero distortion. For large enough n, I can drive this error rate down to 0 as long as I'm not trying to push more than this much of information through the channel. If I want to try to get more information through the channel, I'm going to suffer some distortion such that my error is non-zero. Avnish.
But I mean, you can always have the case where you can never push it to 0, right? Because you can always have the case that everything is corrupted, probabilistically.
No. So there are simple examples that you can cook up where there is some error in your channel that's probabilistic, and you can make an encoding scheme that is readout error free. And I can show you one of them if that's helpful for how this works. Now, it doesn't mean that that error goes to 0. It means that I have to reduce the capacity, that capacity of what I can push through there is less. So one of the examples that's usually given for this is called the noisy typewriter. Has anybody heard of the noisy typewriter? Right. I hear one. You are shaking your head yes, but everyone else looks a little. A Wenping? Okay. A noisy typewriter is like super hipster old school. Okay. So you've got 27 characters. You've got a space, A, B, C, D, Z, and this is just the same space here, okay? And it's a noisy typewriter. So have anybody ever used a typewriter?
Yes.
Yes, everybody's used a typewriter, like a real one, not a keyboard, where you push buttons and a thing that gets stamps ink onto a page. Sometimes if you have an old crummy one like my grandma used to have, and she made me type when I was little because she was a strange grandma, you would hit a key and like 3 things would pop up if it wasn't oiled properly. So what the noisy typewriter is kind of like that. So if you hit A, there's a 1/3 probability. So this is the input. Let's call that X, and this is Y. And the output has the same vocabulary. So your actual typewriter on your laptop could do very strange things, but a mechanical typewriter can't really. So it has a 1/3 probability of giving you an A, a B, or a space. And it's the same for every single letter here. So Z gives you, with a 1/3 probability, gives you Z, with a 1/3 probability gives you Y, and with a 1/3 probability gives you space. So this is the noisy typewriter. You input space through Z, you get out space through Z, but you've got this confusion. So Avnish, I think what you're asking is, you're saying, I can't get rid of this. So isn't there always some probability of error? There is always going to be some probability of error if I try to drive this at log 2 of 27 bits, right? If I want to put 27 inputs and get clean 27 outputs out, I can't. But I can make something that's non-confusable. Because I can say, I don't really have 27 characters, I have 9. And they're non-confusable. Okay, so I drew this dot. So if I say, I don't have space AB, I just have A. And I don't have C to E, I just have D. So I have to communicate with a much smaller vocabulary. I have 9 things I can say. My capacity of this channel is log 2 of 9, and if I want to send that much information or less through, I can do it with absolutely 0 error, without having to appeal to large N or anything like that. Now, I can't send the whole alphabet through, but I could make a repeated code where I knew that if I hit A, that meant A, and if I had C, a B, that meant B, and then my probability of flipping would have some, I could get around a little bit, some of that. I could make a repeated code. There are better codes that are called Hamming codes that let you actually correct errors like this.
this the space A and B and the Y, Z in space.
Oh, sorry. I should have said WYZ. I apologize. I just was WX. Yeah, no, I wasn't trying to make the overlap. Apologies. Good catch. Yeah. Simon.
So this example builds on the fact that you have certain transitions that just have probability 0, such as A to C.
That's correct. You're right. This is what we're sketching here is a very simple case of a non-confusable subset. Now, in general, you might have this. So the A cannot make D. And A can't, only those arrows work. If you have it stretch out all over the whole typewriter, then things get more complicated. And thinking about this non-confusable subset gets a little bit more tricky. In general, what you're trying to imagine is the chunking of space such that your error ball, however I have to, sort of reconnect things so that they're in this high dimensional space, your error ball around there is what you call one symbol. And this example is used in textbooks because it's really clean and easy to say they're next to each other.
Right. But I mean that's basically an point, right? That
Yeah.
If you have a connection to every
Yeah, if there was some noise that would no. What's interesting? Yes, you have to the statements that are made in source coding and the source coding theorem and the channel coding theorem are that you can drive your error to exactly 0 at infinite n, but that there always exists an epsilon that's so astronomically small at finite n that you can win. So this is a case where I can drive my error to 0 with nothing but yes. If I have a general case where there's some probability that no matter what the output is confused, the point is that you can find a way of partitioning the space in these non-confusable subsets and basically deleting the independent sort of vocabulary words that do get confused. So you can make one of these codes by expulsion that you can actually carve up this space to, age of the universe error type thing. That's what we care about. When I compress a file, I don't care if I do it 6 trillion times, I get one error. I care about if I do it, sort of day-to-day regular human scale times. Did I see Liam or not?
Yeah, but I'm happy.
You're happy now, okay. Marco? I'm Leo, I'm just basically just discriminating against you, but I'll come back to you.
Do Neros actually use like redundancy for like error correction?
That's a beautiful question. Can you hold it for just a second while I get through a little bit more of this, and then we're going to talk about some simple channels, and we'll talk exactly about that. Very good question. Leo?
Yeah, I'm just asking if the log 9 base 2 is what the critical value is?
The capacity of this channel is log 2 of 9. That is exactly the capacity. That is the limit of uncorruptible error-free transmission we can do in the noisy typewriter when it's not repeated. Now, if I can have many instances where I have a code that says, when I type 10 things, you have a readout of it, I need, then you make these composite, hard-to-draw, repeated channels, and then you can do more sophisticated things.
Channel capacity, is that a rate or is that what kind of?
Let's go talk about that. I'm going to try to stay over here because I killed that board a couple days ago, so yeah.
We all covered up.
I know, and I said it out loud.
You were recorded when it happened.
Yeah, I know. So it's if they want to get me, they can get me on more interesting things than that. All right.
Drinking in open space.
Like drinking in open spaces. So here's the. Okay, I'm getting silly. All right, so here's the free lunch part of this theorem. The free lunch part of this theorem is that this special point, the capacity, where below that info rate you can send error-free signals, is equal to the maximum of the mutual information between X and Y, the input and the output of that noisy channel. And what are we maximizing over? P of x, typically. So here's the input to the noisy channel, x. Here's the output, y. So we know that the mutual information between x and y might be something we want to maximize if we're sending messages down a noisy channel, which is what we did last time. We maximized that. It turns out that that is also the capacity. That is the point at which you max out the information you can send through the channel, and below that you can't. Now it might seem, because we're saying this, that that's obvious, but because of the way we built it up, but it's not. This is just the info rate. This is how much information I can read out of the channel. It didn't have to be related to the mutual information here, but it is. So this is a number of bits I'm sending through the channel that have readout bit on the other side, and it turns out that mutual information is the right way to think about it. So that's extremely useful. So we had an example before, and I'm going to put it right here. We had an example last time of the response of the neuron is some nonlinearity on the messages plus the noise. So what was our input? What was x? M, thank you, M. This is the input. What was the output? R. That's the output of the neuron. So in this notation, the input, M is x, output is y, and what's this guy again? Noise, good. Okay, input, output, and noise. And what we were trying to do was to find a phi of m that maximized our information transmission by making P of r flat, because we said P of r uniform is the maxent distribution. That's what's going to maximize this info. So how do we muck with phi of m? So when we did that, we were maximizing the information through this channel. But imagine instead that you get to play with the message distribution. When you play with the message distribution, you're doing channel coding. You're saying, I know there's some noise, so I'm going to rearrange my messages such that when I send them through, they're readoutable as possible. Just a way to get your mind running on these things. I wanted to follow up on one thing here. So info and a Gaussian channel. So we can write down the, sorry. Hold on a second. My notes are confusing me. What the heck was I thinking? What was I thinking? Okay, so if the noise is independent of the message, let's imagine that we just had R is some message plus, R is just some message plus C. I'm going to change these notes because they're confusing me. They're probably going to make you miserable. So let's say that M, let's try this case. R is just M plus Z. And let's say that the variance of Z is sigma squared and the variance of M is sigma M squared, sigma Z squared, okay? So M is our signal, Z is our noise, and I've just made it a little bit simpler. I've gotten rid of this nonlinearity, okay? So what is the variance of sigma, what is the variance of R? Remember, this noise is independent of the message. It's really noise. You just add them up, yeah. This is not, I'm not trying to be tricksy here. So it's just the variance of the messages plus the variance of the noise. So one thing that were in the exercises, which I am posting solutions to pronto, was to show that the maximum entropy distribution, remember we're trying to maximize this, with constrained mean and variance. So if we have this simple sort of linear channel, and it's got our output response has to have this variance now, right? It's constrained to have this variance. what's the maximum entropy distribution? It turns out it's a Gaussian. So if you do exercises 2, you will prove that to yourself. And you will also compute the entropy of a Gaussian. So what is the entropy of a normal distribution with, say, 0 mean? Doesn't matter what the mean is. Mean can be anywhere, translation and variance of entropy, and variance sigma squared. Did anybody do that exercise?
Everybody.
Everybody did that exercise, so you all know the answer. And the answer is weird. It's 1/2 log 2 pi e sigma squared. Why is that like that? It's like that because, yeah?
So why did you assume the input was Gaussian?
No, I just said it had variance. I just said it had this variance. I didn't say it was Gaussian.
Oh, you imposed that the variance is...
I said that the variance of the output is this, and if I want to maximize my output entropy, it's going to have this variance, and the maximum entropy distribution on the output is this. I haven't said anything about the message distribution, except for its variance. It could have higher order moments, but this will be the max ent distribution for this output variance. It's a very good question. It's a really important point. I haven't said everything's Gaussian. This is Gaussian, and I know that this is going to set my variance now, because I just made this channel linear. And this variance, to maximize my response entropy with that variance, I know I need a Gaussian. Now, 2 pi e comes from doing Gaussian integrals. You guys have done these before. It's just, if it's rusty, just refresh. Yeah.
So
You're not happy.
No, I'm happy. But you're trying to maximize the mutual information, not the entropy of the output. So there's a...
But remember that we already said that if we maximize the entropy of the output, we maximize the mutual information.
And that's only because the noise is stimulus independent.
That's correct. That's only for this case where I have additive independent noise, where the noise doesn't depend on R.
I guess, isn't it always true when the noise entropy is always constant?
No, yes, this is, it's not always true if the noise entropy is constant, but depends on the response value. I could have variable noise depending on what, on that could sort of like bleed into
That's
this.
what I mean by constant. I mean like it doesn't depend.
Yeah. If it doesn't depend on the inputs in any way, like it doesn't vary with your response state, then yes, then this is generally true. And I just made it simple here so I can just write down phi of m because I don't have to go through sigma of m. I'm assuming that this nonlinearity could be a variance preserving transform and then this all still holds, but it's not true in general that an arbitrary nonlinearity won't preserve the variance of your signal. So that's why I wrote this. Simon.
But a signal transformed by an arbitrary nonlinearity will also have some...
It'll have some variance, so I could say that's now the new... Yes, absolutely. I'm just trying to get away from the we're setting phi, but absolutely. It'll have some variance, and it'll be independent, and we'll add it up. So now, this is the maximum entropy that we can have, and we said that the mutual information between R and M was the entropy of R minus the entropy of Z. So now we just calculate this. So what's the entropy of R? Well, it's a half log 2 pi e. There's a minus sign out front, sorry. Well, no. Apologies. 2 pi e. And what's the variance of the response? It's just sigma m squared, it's just the sum of the variances. And then what's the entropy of the noise? Well, the entropy, we said it's a Gaussian channel, so it's Gaussian noise. So it's just a half log 2 pi e and then sigma z squared. Okay, good. Now we simplify. The difference of the logs is the log of the ratio, right? Add up logs, log of the product, take difference of logs, log of the ratio. So now we have a half log. The 2 pi e's cancel, thankfully, because who knows what the heck that meant. Sigma m squared plus sigma z squared all over sigma z squared, half. And that's a half log 1 plus sigma m squared over sigma z squared. Why is that interesting? Because that's the log of 1 plus the signal to noise ratio in the channel. And that's a really important fundamental result of channel coding theorem, channel coding in general, and in neuroscience. If you have a Gaussian channel, the maximum info, so the capacity of that Gaussian channel, this is the max, so it's the capacity because it's the max info. I don't know why I put parentheses, whatever, is this. That's where the exclamation point should come in. Okay? The only thing we can control in this case, we have the noise that we're stuck with, and then our response entropy that comes from, we said we want to make that max entropy distribution because we're stuck with this. So this is what we're maxing over in here. Now, then we went through and we said, what does the nonlinearity have to look like so we get that response entropy? And we decided yesterday that we were stuck with the distribution of the messages. But in channel coding, the brain over evolutionary time, or if you're an engineer making a communication system, you get to muck with the messages and their distribution. Okay. But this is the channel capacity for a Gaussian channel. 1 plus the log of the signal to log of 1 plus the signal to noise ratio. All right, I'm going to move on, and I'm going to move on to some simple examples of the kind of canonical things you look at in this rate distortion theory. And we're going to move on from there, and we're going to talk about Marco's excellent question about what does the brain do. Okay? Good. All right, so I'm going to throw this up here. Does everybody have this? Getting rid of it. Actually, I'll leave it there, and I'll erase this. So let's consider a simple binary channel. And we're going to consider an input x and an output y. And this time we're going to be living kind of like we're inside the brain. We're inside the brain, so it's neurons talking to each other. So there's a binary input and a binary output. Or you could think of it as there's an external world that's binary. Maybe it's day or night, or some molecule is there or not. Any way you want to think about it. The point is that we've got some input x and some output y, and they're both binary. So x can be 0 or 1, just two states, and y can be 0 or 1. Now, in a noise-free channel, if we sent a 1 in x, we'd get a 1 out in y, and if we sent a 0 in x, we get a 0 out in y. And this is how we hope most of our computers work. Everything is noise-free. But imagine for a minute that you have some amount of bit flip noise. And bit flip noise means that as I go through this channel, I have some probability of flipping one of these input bits from 1 to 0. And it's called a binary symmetric channel. So you can imagine that the probability of flipping the bit 1 to 0 or 0 to 1 is the same, and it's f. There's some flip probability. So what's the probability that 0 goes to 0? Very good. 1 minus f. It's a binary symmetric channel, so the probability of going from 1 to 1 is also 1 minus f. Very good. So now, let's assume that the bit flip error f is 0.15. That's kind of a reasonable number for biology. I just chose it arbitrarily. But there's kind of a 15% chance that things get screwed up. So it's big, but it's not crazy. So now, what is the channel capacity? What is the channel capacity? Well, we learned that the channel capacity is the max over p of x of the mutual information between x and y. So how are we going to do that? Well, the p of x that we're going to choose is two values. It's p of 0 and p of 1. Right? Now, without taking any derivatives or doing anything fancy, we can just look at this and say that it's got to be half a half. Because this channel is symmetric, and just by symmetry we can say that this we're going to guess is a half. And you can prove to yourself that that is the case. So then we want to know what is this max mutual information between x, y if the probability of the input is a half. If we use, sort of maximum entropying x and using each of those equally. There's nothing special about 1 versus 0. So we better not waste information by biasing it. So now we want to know what's this mutual information, what's the capacity? Well, that's just the entropy of y minus the entropy of y given x. Why did I write it that way? I wrote it that way because it's a little bit harder to write the entropy of x given y in this case. But we can compute the entropy of y. What is the entropy of y? Well, let's examine one thing. Think for a second, what's the probability that y equals 0? Think about it for a second, and then we'll do it. What's the probability that y equals 0? How many ways are there to get a 0 output? Two. There are 2 arrows pointing to that 0. What are their probabilities? Well, it's the probability that x equals 1, right? Whatever that is, times what? Times f, times the bit flip error. And there's the probability that x equals 0 times what? 1 minus f. Very good. Okay. So what did we say we're going to say p of x is? A half. So here's the point where you could write all this entropy out, and then you could take derivatives with respect to p of x and figure out that the maximum is a half. But by symmetry argument, we've said that's what it's got to be. So now we can just plug it in. So this is f over 2 plus 1 minus f over 2. And what does that equal? A half. Okay. So what's the probability that y equals 1? Don't have to do anything. If that's a half, 1/2. Very good. So what's back up here now? What's the entropy of y? Y is a half. What's the entropy of a fair coin? 1 bit. 1 bit. It's minus a half log 2 of a half times 2. Minus log 2 of a half, log 2 of 1 bit. So it's 1 bit minus s minus the entropy of y given x. So let's do that one. What's the entropy of y given x? So given that x is 1, y is 0 with probability f, and 1 with probability 1 minus f. Given that x is 0, y is 0 with probability f, and 1 with probability 1 minus f. They're symmetric. Those things have equal probability. So our entropy of y given x is just the entropy of this distribution. Let's make sure I got this right. Yep, f and 1 minus f. Just the entropy of that distribution. So that is minus minus f log f minus 1 minus f log 1 minus f. Okay. That's something. I'm just going to tell you that now the mutual information between y and x, or x and y, is 1 bit minus, if you run this through for f is 0.15, you get 0.61 bits. So that's a channel capacity of 0.39 bits. And if we draw it, xy as a function of the probability that x equals 1, and that goes from 0 to 1. It's symmetric, and it's maxed here at 0.39 bits. So if we change f, we'll modulate this symmetric little humpy thing up and down with a different peak, but the peak will always be at a half. All right. Okay. So if neurons worked like this, you would have max information transmission when your probability of a spiking was a half and your probability of not spiking was a half.
Can you maybe comment with how do you actually send through this channel an error-free message?
How do you send through this channel an error-free message? Right. So what I'm saying is that there's 0.39 bits of information. So I can't get, if I send a 0 or a 1, I can't reliably get a 0 or a 1. So to send an error-free message, I would need to make repeats of this channel. And then I'd have some probability of the bit flip error screwing it up. Does that make sense? Okay. But I'd have to sacrifice something by having to say, I'm going to, instead of sending just 1 0 and crossing my fingers and hoping it doesn't get flipped, I could send several zeros. I could make a repetition code. And then I know that the probability of many of them getting flipped would be, I would get a multiplicative thing there. And so I could read out based on how many got flipped, I could do some error correction. Now you can do fancier error correction with a binary symmetric channel like this, where there's some probability of bit flip error, where you do something that's called a parity check code. And I could compose several copies of this binary symmetric channel in a way that I could do a Hamming, how does it go? It's called a Hamming 7-4 code, right?
Yeah, but that's not this one is not capacity achieving.
This is not what, sorry?
Capacity achieving.
Capacity achieving. No. This is not, this just by itself has a capacity that if I just send zeros and ones, I can't get it. I have to do something to it.
Yeah.
So that's its capacity, but the channel coding theorem doesn't tell you how to make that code. And that's sort of what's hard about that's why there's a whole industry of how do you make codes, and that's why the Hamming code with parity check was such a big deal. That's why low density parity check codes were a beautiful thing. Shannon proved back in the day that you have limits, that you have some, sort of limit of the minimum error you can get as a function when you go beyond your channel capacity. He said, oh, this is bounded by something. But he didn't say how you would make a code that achieves it. And that took decades to figure out. And David Mackay was one of the people who did a lot of that work. Okay, so again, this is the info rate in the channel, and this is the capacity, and you can't do this. So what Shannon said was, you can get an error rate down to here, and nobody knew how to do it. So you can sometimes even compute this capacity, and it's not obvious how to make your channel work for you in that way. You have to do other things to it. Okay, so let's talk about something that's a little bit closer to neuroscience. So instead of a binary symmetric channel, let's make things asymmetric. So I just told you that your input distribution should be, you should use bits 1 and 0 equally in this binary symmetric channel to max your info rate. But we know that neurons don't fire all the time. You do not find neurons that have a 1/2 probability of firing. Neurons fire sparsely. So to get something that's a little bit closer to neurons, we're going to talk about the Z channel. So Z channel is just another binary channel. So we have inputs that go 0, 1, and outputs that go 0, 1. And again, if we had perfect transmission through the channel, it would look like that, and its capacity would be what? 1 bit. Right, exactly. if we have no noise in the channel, we know we can send 1 bit down this channel. And if we repeat it, we could send lots of bits down the channel. Okay, but here's what the Z channel does. The Z channel says there's some probability of F that 1s get flips into 0s. So the probability of keeping your 1 is 1 minus F, and the probability of sending a 0 is noiseless. Why is this more like neuroscience? It's more like neuroscience because you have your noise in the biological system is about failure of vesicle release, not about uncontrolled dumping of lots of transmitter. It's about the failure of the vesicles to get through the synapse and to have you to have sent enough message. You don't get sort of noisy. You don't get noisy spikes. You get kind of noisy failures. It's one way of thinking about it. Now, this gets into a more nuanced point, which is that what's called noise in the brain doesn't have to do with just the noise of sending something across a synapse. What people call noise is sometimes everything else in the brain that you couldn't control. So when we talked about that bird singing, what we decided was being controlled was what he sang, and we even warped things so that we had like kind of the same song, rendition to rendition. But of course he had a different posture. Male bird might have been had been in a different brain state. He might have been paying more or less attention to the female. He might have been looking at a different part of the female. There were all kinds of things about that bird's brain that we were definitely not controlling. And so when we saw trial-to-trial variability in the spike times, it could have been failure of vesicle release at the synapse. More likely, it was that on a trial-to-trial way, his brain state was fluctuating because all of this other stuff that we weren't controlling was fluctuating. A little diversion, but I want you to have a totally cartoon picture of how complicated the brain is. All right, but let's come back to this cartoon picture of how simple the brain is, how simple the brain can be. So we have this Z channel. So what's the information in this channel? Again, the information, mutual information between input and output is the entropy of the output minus the entropy of the output given the input. So now I have my P of X, and I'm going to call that P0 and P1. And there's no symmetry argument here. It's not clear what I should use more or less, right? Now, you might have a notion. What do you guys think you should use more? Just from looking at it. Don't try to calculate anything in your head. Just which of these symbols on the input should you use more? The 0. Why? It doesn't get flipped. Now, if you use that more, you'll probably have more reliable information transmission. That's exactly what we're going to derive right now. So, good. Obvious thing, but let's derive it. Because this will show you a basic strategy. We'll start the calculation, and then you can finish it in the exercises. So what's the entropy of Y? The entropy of Y, so we need the probability. So we need it's related to the entropy of the probability distribution of Y. So we need the probability that Y is 0. What's that? What's that? Well, it's the probability that X is 0 times 1 plus the probability that X is 1 times what? F, right? And what's the probability that Y is 1? Well, that's the probability that X is 0 times what? No. So if, right, sorry. What's the probability that Y is 1? I did the wrong thing. It's the probability that X is 1 times what? Yes, you were right, it's 0. 1 minus F. Thank you to everybody who got the right answer and got the right answer because they were error correcting for me. Okay, and is there anything else we need here? No, there's nothing else we need there. So let's rewrite this. Let's rewrite P of 0. Well, we know that it's just 1 minus P of 1. Okay? That okay with you? Okay, so the entropy of Y is the entropy of this distribution. We've got a 1 minus P1, 1 minus F, and we've got a P1, 1 minus F. So it's just the binary entropy of these two states. So that's just this log this negative sign plus minus this log that. Okay? I'm just going to leave that there for a second. So what's the entropy of y given x? What's the entropy of y given x? Well, that's the entropy of y given that x is 0 times the probability that x is 0 plus the entropy of y given that x is 1 times the probability that x is 1. Right? Does that make sense? Good. So, what's the entropy of y if x is 0? If x is 0, what is y? 0. Always. Never changes. What's this entropy? Very good. 0. Okay. What's the probability that of y given that x is 1? Well, let's write that out, right? So here we've got 0, and then we've got the probability that x is 1 times the entropy of y given that x is 1. So I'm going to call this a binary entropy again because y is just 0 or 1. So what's the probability that y is 0 given that x is 1? What's the probability that y is 0 given that if x is 1? F. Great. What's the probability that y is 1 given that x is 1? 1 minus f. Okay. So here I've got the entropy of y given x is P1 times the binary entropy of F1 minus f. Okay. So now we have the information between x and y is we've got the binary entropy of 1 minus P1, 1 minus f, P1, 1 minus f, minus the entropy P1 times the entropy of F1 minus f. That is the information in the Z channel. Now, what are we trying to do? We're stuck with f. We're stuck with f. So we want to take a derivative with respect to P1 and set this equal to 0 because we want to maximize the information transmission. Okay? I'm going to leave you guys that as an exercise so that we can move on and talk about more interesting things. I'm going to draw the answer, and the solution is in the solutions to the problem sets. So here is, on the x-axis, this is probability that, this is P1, the probability that x is 1. So that varies between 0 and 1, and here is 1/2. And here is the mutual information between x and y in the Z channel. So for the binary symmetric channel, we have that the information was maximized when P of 1 was 1/2. What we find in the Z channel is that it's maximized somewhere over here. Okay? What does that mean? It means we use the 1 less. We use the 0 more, just like you guys thought. And the curve looks something like this. Curve looks something like this. That is an f-dependent statement. This is for some particular f. Because obviously if f goes to 0, come back to 1/2. Come back to 1/2. So you will do this in the problem set for a particular f. Let's say, f equals 0.1, something like that. Okay. So that's just a little bit of that is your lightning fast intro to info theory in the brain. So what I want to do next is to talk to you about what you can do with information theory beyond this sort of foundational stuff. So this is more current research in info theory that has to do with adding particular behavioral computational constraints to these problems. So this is going to be a little bit more maybe a little bit. We're not going to calculate anything at the board because it takes a long time. I have given you an exercise set for calculating some of the things that are in info bottleneck calculations, and I've given you a very detailed LaTeX solution set so you can look through that. So what I'm going to do is I'm going to take one of these information coding problems and say I want to maximize my information about the external world, but I don't want to maximize it arbitrarily. I don't want to keep everything. I only care about some particular variable. So I don't care about everything that's in the message. I want to be able to define particular parts of the message that are relevant for downstream computation. So to do that, I want to tell you a little bit about why the brain needs to make predictions. So processing delays in your brain mean that what's happening right now in your brain lags significantly behind the state of the external world. And this is true for all organisms. And that means that if you have even just a modest, like 50 millisecond lag, that if you're trying to interact with the world as it's moving quickly, like Serena is doing here, maybe this is a 60 mile per hour ball, she's going to be off by several feet if she doesn't compensate for that even modest 50 millisecond lag in her eye. And that's just her eye. That's not even saying, you know, how long it's going to take her to drive her arm to hit that ball. And even those of us who are really bad at tennis can get our racket on a ball if it's traveling at 60 miles per hour. We can't put it anywhere reliably. I can't put it anywhere reliably, but we can get our racket on it. So we can interact with fast-moving objects that are moving faster than the sensory and motor delays in our system would nominally let us do. So that means that the brain is constantly making predictions, and that information that's relevant for the future of your inputs is really important to retain. And that maybe, we're going to take this further, we're going to say maybe the brain is optimized not to represent everything about this scene, but just the bits of it that are relevant for prediction. So if you look closely here, you'll see that Serena is not looking at where the ball was. She's looking at where the ball will be. And professional athletes do this, and we also do this. We anticipate. We go beyond just compensating for sensory delays and looking at veridically where this thing is. We actually look at where it will be forward in time. So I want to, am I going to play the, yeah, we don't really. I'm going to skip a little bit of fun in the interest of telling you something more concrete. I apologize. Okay, so what we'd like to be able to do is then to be able to interrogate this in natural scenes. The trouble with natural scenes is that they're really high dimensional, and group 10 is looking at a natural scene just like this and trying to figure out how to reduce the dimensionality so that you can ask how well do, say, neurons predict where these fish will be or where these leaves will be. But the way that we set up the problem was simpler. We said, how well can the retina predict where this bar will be? Okay. It turns out that the retina is a really, really complicated piece of neural tissue. These are data from Thomas Euler just showing all the different cell types you have in the retina by their functional classification. So what they do here is they play a whole mixture of different things to the retina in a dish, and they ask, how do those neurons respond to fluctuations in color, fluctuations in contrast, and all sorts of things like that. And they find that they can, you know, depending on whether they feel like they're being lumpers or splitters, they can have, you know, 50 different cell types in the mouse retina. And as sort of physicists, we'd say, well, that sort of complexity is not going to exist in the eye unless it's there to do some computation. And indeed, it's there to do stuff like this, where in red I've plotted kind of the neural image, how many cells are firing at a particular position on the retina when a bar is flashed over that part of the retina. So there's kind of like this red hump of activity in the retina around the real bar position. But when that bar moves in from the left, you see that neural image is shifted towards the leading edge of the motion. So that if you were downstream of the retina and trying to decode where this flash stimulus was, you'd be correct, but you'd have a lag. Whereas if that stimulus is moving, you're anticipating where that motion will be. Retinas do all kinds of crazy stuff like this. They also respond to motion reversal. So if a bar comes in and then reverses course, across many cells you get a synchronous volley of spiking from the retina. And that could be a pretty fun signal to send downstream to say update your prediction process. All right, so let's get into a little bit of the nitty-gritty here. So what are we going to do? So we created a bar stimulus with both predictable and non-predictable motion components. And here's why we did this. If you want to know if a biological system predicts, you can't just give it a deterministic stimulus and then talk about how much it encodes the future, right? Because if it's completely deterministic, then you have a confound, because if it encodes what happened just now, you can read out what happens in the future, and you don't know what the brain or the biology cared about. So what we wanted to do here was to give some information to the retina where we said, here's predictable stuff and here's non-predictable stuff. We know the retina is going to make a compression. So here's the predictable, here's the non-predictable. It could compress, so throw things away equally, to make a compressed representation of what was happening in the external world. This is predictable. If we think that it cares more about this stuff, then as it compresses, we expect this non-predictable stuff to preferentially shrink. And if you don't give predictable and non-predictable together, you can't tell if I have this much information about the predictable part because that's how much I compressed, or it's because that's how much I care about the predictable part. You have to do this together. So we made a really simple stimulus. It's something you guys have probably seen in high school. Well, you probably saw pieces of this in high school. This is a dv/dt is minus v over tau, and then there's omega naught x squared. So v is the velocity of the bar, x is the position of the bar. That's just a damped harmonic oscillator. You're all probably having like qual flashbacks from. And then this is noise. So without this, this is just plain old Brownian motion where you've got mass, so you experience some drag. And here is in a potential well. So you can think of it like I've got a damped harmonic oscillator that's getting driven by stochastic velocity kicks, or I've got a Brownian particle in a potential well that has mass. Those are the equivalent. The nice thing about this is that we know how to solve this to death. We can do a ton with it. So there's the distribution of positions that are explored by this bar. It's in a potential well, so it's confined. That's good for neuroscience because we are showing this in a dish, to a retina in a dish. And if the bar just wandered away, we would have a whole segment of our recording where there was nothing happening, and maybe it would wander back. These are the predictable components of the motion, and we set it up so that they have an order of magnitude difference in their time scales. So the prediction is nuanced, and that's the noise. So that's the non-predictable part. This is just an example trace of the position of the bar as a function of time, and this is the correlation, position correlation function. Okay, and then I showed you this before. What we do is we take a larval tiger salamander, a big thing, and we chop it up and put it in a dish. Liam.
Maybe this is a stupid question, but is there like an idea of natural emotion as equivalent to natural seeing?
I feel like I planted this question in your brain. It's so wonderful. People have done a lot on what is a natural scene and what are the statistical dependencies of that. People have quantified a little bit previous to us about what natural motion looks like. And we just created a 2 terabyte database of lots and lots of scenes and did a bunch of analysis of motion in those scenes to categorize them and say what the important statistical features are of natural motion. Important statistical features that you can already guess are things like confinement, active transport, because a lot of objects in biological scenes are, little organisms themselves. They move around in particular non-diffusive ways. And you also have fluids that are turbulent that move stuff around.
My concern was just that, if you're giving a neuron or something like to bar stimulus,
Yeah, this thing's too simple maybe.
or like too stochastic.
So we have to play around, and we did play around, so this took several years to get right. Yeah, there were a lot of experiments that went into it, a couple years to get this right, where you have to vary the noise distribution so you get a good velocity distribution so that the speed distribution is relevant to that particular piece, to that particular retina. so we made the bar size and the bar speed distribution, we set all these parameters so that that salamander retina could see it and would respond to it. You're right that this isn't necessarily supernatural, but it is in a little, at least it's physical. At least it's a bar with inertia that's getting some random kicks. Maybe that's like wind, and it's it's tethered. So maybe it's like you could think of this as like a model for a leaf or a twig blowing around in the breeze. I don't want to say that too strongly because, of course, turbulence has correlation times in the noise and blah, 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 and it's not in there. So we will like to push on this, but it's not a bad first place to start, and the retina really likes this stimulus. Lots of spikes. Yeah.
So how do you distinguish between memorization and entropy?
Absolutely. That's great. So let me repeat your question and riff on it a little bit. So how do we distinguish between remembering the past and predicting the future? Well, what we want to be able to say is how much of, all right. The thing is here, we can't dig into that too far because this stimulus doesn't break time reverse invariance. This is time reverse invariant. So if I remember this much of the stimulus, I can do just as well predicting the future as I can post-dicting the past before my memory window. What we're going to do, the calculation we're going to do, says, given that I have this much information in the retina, how much can I say about the stimulus in the future? And yes, the neurons could be using that to have some later on post-diction of what happened before. And we're just making appeals to what we know about biology and behavior to say we think it's something to do with prediction. You'll see some asymmetries in some of those things we calculate from the retina. Okay. All right. So this is the experiment. You take you sacrifice the salamander. Under dark light, you dissect out the retina, and you carefully press it onto a dish full of recording electrodes. These recording electrodes are really finely spaced such that the density of the recording electrodes is on par with the density of the cells from the retina. These are the retinal ganglion cells. They're like a monolayer in the retina. So this makes this sort of like begging to be recorded from in this linear array kind of way. And all of these bundles are the output wires or axons of those ganglion cells flowing towards your blind spot, where they push through your retina. So you've got a blind spot, you can find it and move your finger around, you guys have all done that. You have a blind spot because your retina's flipped, your ganglion cells are on the near side, in by your vitreous, so all their axons have to go through to get out the back of your eye somewhere, and they go out, and that creates your blind spot. So that's what all these things are. So if we get a good recording, which I've done a few of them, so they're easy enough that a theorist can do them, but Olivier Marr is really the person who collected the majority of these data that I'm going to show you. So he has really good hands, and he could get the retina on the dish just so that we could see what the brain sees in this part of visual space. Because the retina's the retina's got some topography, so here in the retina is there in the world. So you can, if you get a good recording from here, you know what the brain sees there. All right. And we get these little blips are just those spikes that we talked about in the first lecture. And we're going to make everything binary because that's what we do. And here occasionally we might have 2 spikes in a bin. We're going to bin spikes at 20 milliseconds. And we just make sure that there's less than 1% of the time that happens. And now, so our fundamental data are these binary words, and this is just their decimal representation, as a function of time in that stochastic bar movie. And we're going to ask, how much does the retina know about the future of the movie or the past? And is it as good as it could be? And to answer the question, is it as good as it could be, we're going to use information theory. And we're going to have to add this computational constraint of doing prediction to what we've been doing so far. Okay. So again, here's a schematic of our calculations. This is like the 1D position of the bar fluctuating in time. Here are all our little binary variables, sigma I. These are the different cells in the retina, and they spike. And we can compute how much information the retina has about the past of the stimulus. That's like the R log R calculation we did before. You can do that here. So all that laborious stuff we did, you can do that here because we're going to play a long bar movie, but we're also going to repeat it. We also want to calculate how much the retina knows about the future of the stimulus. To do that, we need to have the same future without repeating the past, because we want to have repeat many times the same future, but with different pasts. So we do that. How much the retina can possibly say about the future is constrained by the correlation in the stimulus itself. Of course, there's no fortune telling. There's no free lunch in the brain. So that's why we picked such a simple stimulus, because we can compute all that stuff. And we can say what the optimum would look like, and then we can ask if the retina is close to it or not. So that's the procedure. We're going to go through and we're going to say, what's the mutual information between, say, past of the retina and future of the stimulus? Well, that's just our uncertainty about what the future of the stimulus could be, minus our uncertainty about the future, given that we observe the retina in the past. So here is a simple way of looking at this, which we're not doing info bottleneck yet. We're just sort of tracing out how much does the firing of the retina, that binary word at time t, say about the position of the bar at time t plus delta t. So here I've aligned everything at 0 is where the cell spiked, and here's a more realistic time trace from that movie, and this is from our 2015 PNAS paper that's in the readings folder. So we said, how much does the retina know about something that happened almost a second in the past? How much does it know about the stimulus like a second back? And it's not very much, it's close to 0. How much does it know about 300 milliseconds in the future? Again, not very much. It's just one neuron in the retina. But as we get closer and closer to the time where that neuron spiked, we have more information. And that's for one cell. This is for the average over all 1 cells in the recording. Now, I calculated this as bits, but then it's bits per spike, so I've divided by the entropy of the response. So for one neuron, that's just dividing by its firing rate. But if I do 2, 3, 4, 5, 6, 7 cells, then I'm just dividing by the entropy of that, say, 2-cell group or 5-cell group. So what you see here is that when I average over many groups of size, say 7, I have a lot of information about the stimulus position, a little bit with a lag in the past. It's hard to see here, but this lag is getting like sort of sucked up as I increase n. I have information that bleeds into the future, and I have information in the past, and it's asymmetric. I have more about the past than I do about the future, but I do have this information. Now, why does this go down? That goes down because the information that the 3 cells and 4th cell and 5th cell are contributing is redundant, because it's the information per spike. So it's going down. That relationship nearly flips over as you go into the future. Caroline?
I was going to say, it looks like it flips.
It looks like it flips. It indeed looks like it flips. It looks like the neural code is almost synergistic, if not independent, about the future. So it seems like the retina is trading off redundant information about the past for independence or sort of maybe maximal information about the future, and we don't have a good theory that says why that should be and what that means yet. So this is just for position. There's position and velocity. When you put those things together, you see these curves jump forward even more so that this delay is actually absorbed, which is pretty fun, but it's just a little bit harder to visualize and a little noisier. The fact that there's information here about the future should not surprise you, because there are correlations in the stimulus. What we wanted to ask is, given that you know this much about the past, how much could you possibly know about the future? You should always know something because there are correlations, and unless the retina is responding to just the noise trace, it'll have some information about the future. But is it as much as you could possibly have, given that you experienced this much? So to do that, we need to know something about the correlation structure in the stimulus itself, and we need to compare the generalized correlation or information between the response in the retina and the stimulus in the future. So to do that, we're going to use one of my favorite techniques and one of my favorite new images, which is this. This is
And you should all be happy that you are not going to be walking around with a t-shirt.
I'm going to make myself this t-shirt.
Because we seriously considered it.
I might very well make myself this t-shirt because I love it. This is the information bottleneck technique. And we're going to talk about it here, and then I'm going to show you that the retina does this, and then we're going to call it a day. Okay? All right. So here is the bottleneck. Oh, look, it's even green. Oh! Guys. Okay, good. Okay, so what we're saying is that the information about the past is getting compressed into the representation that the neurons in the retina have now, such that they can read out as much as possible as they could about the future. So how do we actually optimize this problem? We're going to optimize this Lagrangian where we're going to minimize this. So what we're trying to do is minimize the information we keep about the past, so squeeze it down, subject to a constraint. So here's our Lagrange multiplier beta here, that we have a certain amount of information about the future. And of course, I'm leaving off another constraint. What am I leaving off? That the probability distributions are normalized. So in the exercises for today, this is constantly swept under the rug. I sweep this under the rug in my own work, swept under the rug in every Tishby paper you read. And I wrote it out for you laboriously so that you can have it. You can have one copy without errors that takes you through a piece of this info bottleneck calculation. Okay? So this is what we're doing. We're saying we want to compress the past subject to keeping some amount of information about the future. Now we could also say subject to some amount of compression, what's the maximal amount of information I could have about the future? So I can either minimize this function or swap it around and maximize that, and it's completely symmetric. So what we're saying here is just I'm trading off compressing the past for retaining the future. And I can think about that in either way. Okay. No, sorry. No. We're not going to do that. It would take another hour and a half. And so that's why the notes are written up. Okay, so this is the function that we're trying to maximize. And the thing that we get to maximize is the probability of response of the neurons, or P of that compressed representation, which is called X tilde or T or X hat, depending on whose paper you're reading. If the input is X, it's some re-representation of X. So what do we get to modify? We get to modify P of that re-representation given X. So P of X tilde given X. And that gives us the optimal trade-off between the past and the future. It gives us this bottleneck curve. And here are the references if you want to look up the details. The gray region is forbidden. No neuron in the brain, no coding strategy can know more about the future than it knows about the past, and generally can't get above this bound. This curve is concave, convex. This curve is convex from concave from whatever the one is where it's positive from above, it's curvature from above. Anyway, this is concave, correct? Thank you. Convex is convex optimization. You go in the bowl. So that's how we'll remember it from now on. Okay, so this is a concave function. What this is telling me is how much have I compressed the past. So at 0 here, I've thrown away everything about the past. I know nothing. So I obviously can't predict the future. Out here, I've remembered basically everything about the stimulus. I haven't thrown anything away. And it can keep going on and on and on and on and on if my noise is some continuous variable and there's just many, many things I could represent. It saturates at some point because that noise isn't predictive. So this is the maximum amount you can know about the future because there's noise and it gives you some limited amount of resolution about the future. So here I knew tons about the past and I could recover as much as I want about the future. This shoulder is a really interesting point because it says where that trade-off becomes sort of has some meat to it. All of this white region is accessible and possible by the brain. So we're going to be really impressed if the retina glues itself to this bound, and we're not going to be so impressed if it sits out here. So this is what we found. The retina gives us access to this part of the bound curve where beta is greater than 1 but not super huge. We want to get into this shoulder region, but we need to have some new techniques to get there. So if we do this, we have information that the retina has about the future versus the past. In this region, it's nearly linear. Slope is just a little bit less than 1. And we want to know, does the retina sit close to the bound or not? Like I said, this gets a little tricky. You can measure the information that the retina has about the past in that R log R way that I showed you already. To measure the information that the retina has about the future, again, you have to repeat the future without repeating the past. Another way to do it would be to parameterize the past and future and just play a really, really long stimulus, and we did that too, and this all works out. So here's what we got. For single cells in the retina, we got some amount of info that was low. This guy that's in the gray region is not violating, it's not fortune telling. There's just some error bars around this estimate. So imagine that this bound has a little error fuzz. That's 2 cells, 3 cells, 4 cells, 5 cells, 6 cells. So then we were happy. We got our PNAS paper, and I got my faculty job. Good. So what this said was that every cell in the retina is participating in a group of cells that saturates the bound. And if I take the textbook picture of what the retina does to encode the outside world, it looks like this, even if I give it as many legs up as I possibly can. This is a linear, nonlinear Poisson model. And that just doesn't get towards this bound. It looks like it's saturating a bound that has about 100 millisecond delay. So that's interesting. So things that we're asking now is, what do you have to add mechanistically to these models to get closer to reproducing the real data? And how does this scale beyond the retina? Are there hierarchy of bottleneck problems throughout the brain? So we're looking at that in a bunch of different ways. And I think it's a really exciting way to approach using information theory in neuroscience, because instead of just saying, how much does the retina carry about the past, and you can see here that this model sometimes even does better than the data in representing the past. So you might not have learned much if you were just compressed along this axis. But here we've guessed. We've guessed at something. We've guessed at a computation that's important for the retina, and we think we got some evidence that it's actually playing out. Yes?
So these flows are time dependent, like on the reaction time of the retina has
So something that I didn't mention is that this future is the future of the stimulus at a particular delay, so it's at about 20 milliseconds into the future. This is for a fixed time. Yes. We found that as a function of that lag, I think this is the chalkboard that I can't really use. So as a function of delta t between the past and the future, so here's like 20 milliseconds right here. Here's the bound. So at a particular amount of compression, so at a particular x point, that bound, as I vary delta t, is going to fall over. That whole curve falls over with delta t. So we're just looking at one point. That's the bound. So you can't get up here. And we found that the retina, at least for some groups of cells, seems to sit here. Which is pretty fun. So, so that's kind of a nice way of looking at the problem. Now, it could have been that we guessed the wrong thing. If we guessed that the retina really cared about the texture, we could put a texture, like a texture on the tennis ball. Does the retina care the most about the texture on the tennis ball? We could have said, what's the optimal representation so that you recover all of the little hairs on the tennis ball? It probably wouldn't have worked. But we should try those things, right? You should, not sort of just look under the street lamp kind of thing. So anyway, this has taken you from the very, very beginning, what's information theory and how do we use it in biology, all the way through to what are the people who are currently using information theory in biology, how are they formulating these questions, and hopefully along the way you now have a critical eye on what the advantages and disadvantages are of this technique and how to push it forward. So let's not just keep computing bits about the position of the stimulus. Let's make a guess about what is relevant to the biology. Maybe this could be a behavior that's relevant to biology. So hopefully you got some tools to at least be good science citizens when you're doing critical reading of the literature. And it's been a blast hanging out with you this week, so thank you. We go to lunch. We go to lunch now. I don't know. I have one more. I have an infinite stash of jokes. I mean, but they get worse and worse. Why was 6 afraid of 7? Why was 6 afraid of 7? Because 7 ate 9. Why was 6 afraid of 7? Because 7 was a registered 6 offender. What comes between fear and sex? Fünf. You thought it was PG-13, but it was not. Okay, and that's really it. That's good.